Okay. Well, let me start now with the lecture of today, and we will continue with the two possible variations, or the variations of Kalman, excuse me, of model predictive control. Now, let me reopen a little bit the presentation. This can help a little bit to recall, but because now, as I told you, we will move to two variations, but they are similar. What we have seen in depth last time. 1 second. But I will repeat a little bit this. Let me share these two variations in order to recall and in order to introduce this topic of today. Last time we implemented this solution, which came from this, let me say, cost function, if you want, which we have a weighted function in terms of weighted part of the function in terms of error, what we want to obtain, yr, the vector of our desired output, and what we predict, y hat, as in a vector again. Basically, is the error squared, the sum of the error squared at each step in the function. Q is the vector which weights let me say the error, because of course the error today is more important than the error probably. If we assume that the error tomorrow, the error in 100 years, the reason is that at each step in this phase, at each year, we will recalculate again the solution. And remember this part here, which weights again step by step, starting from the actual input, the future input, with using a matrix R. Assuming that the control input, the length of the control, let me say control horizon, better to say, equals the predicted horizon. Of course, if they are different, they're different, but if they're different, then nevertheless, the control horizon must be always less or equal the prediction one. The matrix Q and R, they have different dimensions. But let me consider this case here at this moment. This is the analytical solution which I didn't demonstrate in detail, but you can find in any literature and so on. We can see that it depends on the, let me say, predicted error, this part here, weighted, let me say, by this relatively complex part. Do you remember F1 is the matrix which depends, let me say, which depends on the inputs. In particular, Q and R is the weights. I mean, F1 cannot be modified once I have the model. Q and R represent the weights, and this can be, of course, modified. Could be, we can consider different weights. I mean, do you remember I told you exactly now that the error today is more important than the error tomorrow, and so on. This is an assumption for the for R. Also, we assume that very often that the input today must be limited. Therefore, I am considering this Q and R, but in particular, the input today is more important than the input tomorrow, because the input today should be present in the sense I should be able to apply it. You see. Moreover, as I told you, at each time I will recalculate the solution because something changed, because a disturbance appeared. Today we will see the role of the disturbance. The role of the disturbance. Yeah. Let me now go ahead with what I would like to say today. Yeah, the demonstration, we don't need to learn this. Nevertheless, look at this possible variation, even though inside of the frame which I introduced until now. If I assume that UK equal UK plus 1, UK plus 2 until UK plus P, all inputs the same. Of course, this is a little bit strange, this. But the reason is as very often, how possible to say, the input really change. The changes is really very few changes. The reason is very often that the horizon is very short. Very often short horizon, very short TS sample time. This means it's an assumption which can be considered, let me say, valid. Mathematically, of course, it's a little bit strong, but practically valid. And we can see that the matrix F1 becomes F1. Last time I clarified, why it becomes basically this matrix here collapses in this. And in particular, if you have one input, we have just one column. Last time I showed you the reason why is this in exactly this form. Of course, because we have basically just one input for all horizon. And roughly speaking, if I summarize directly everything, it's important because we will see now in the presence of the disturbance, we will come back on this. Now, the variation with the disturbance, or in general, I can consider the variation considering delta U equal UK minus UK minus 1. The reason of this possible variation is that I can consider in the control also the past U. Now we will see a little bit more explicitly because I will reformulate everything in terms of delta U. In fact, we can see exactly in this slide that the cost function now changes. We have the second part, basically the part related to the input, which depends on delta U. But of course, delta U is a function of U, but not only, it's a function also of the past. The change is not only formal, because here appear explicitly the influence of UK minus 1. Explicitly. Of course, in such kind of iterative solution, I mean, step by step, I will recalculate the solution starting from the let me say from the new state. Let me say roughly speaking. This means somehow also in the previous solution I have indirectly the effect of UK minus 1. Here, it's explicit. Is explicit. The problem is solved in delta U, in the increment. Yeah, offer a little bit more, of course, but we pay a little bit more again because now the past input is explicit there. But of course, very often I would like to say, in accordance with my experience, we can tune Q and R more easy in easy form, easy way. I would like to say sometimes I have the feeling, excuse me if I introduce this word, which is not exactly scientific. We have the feeling that the solution a little bit smooth with respect to it makes a little bit sense if you think because we are considering explicitly, as I told you, the input of yesterday, let me say u k minus 1. And we calculate an optimal delta U, an optimal delta U. But of course, an analytical demonstration of this, it could be that there exists, but I don't know it. I never looked at this. Um, yeah, and this is the solution. This is the new problem formulation considering now as an input the past one. What change basically is the matrix F2. Mm. We can demonstrate, I put here also the literature that the matrix F2 is this one. This is the solution, which can be also calculated using the same calculation, but I don't want to be really boring. But we can see this quite similar before. No? Of course, the matrix changes, the structure of the matrix changes because the problem is a little bit different, no? Because we want to look at this delta of the increment. And we have a matrix more, F2, because we have an input more, UK minus 1. What is interesting now? What happens in case of disturbance? Because the case of disturbance is analyzed in the frame of delta. This also, I'm not so expert on this, no? I'm not so expert on this. But this is nevertheless related to this smoothness of a possible solution. The reason is when we have a disturbance, it could happen that you have abrupt changes. Now, a possible approach is to use an approach which smooths this abrupt changes. And that's how it seems, as I told you, I don't have the demonstration. It could be that it exists. Intuitively, we can understand to calculate a delta between the earlier element and the actual one is something more, a little bit more fine than to calculate directly the input. This we can demonstrate this, the solution basically structurally the same. I will add this element here. We can demonstrate that this is one. What happens in case of disturbance? We can see here that we have a disturbance which is in the system through the map D, which is the map of the disturbance. This means depending, this I told you last time, what is the meaning of D? Depends of the structure of the system and depends how I can conceive the disturbance which is affect the system. The map of the disturbance. Remember, last time was 0 first component of the matrix D, and the second component was -1 divided J. Also, today will be the same. Doing the calculation, as I did at the beginning, for D equal 0, now is D is not 0, D not capitalized, disturbance. This is a signal, an external signal. It's an input, but it's an input not accessible. It's not you input. If I do the same calculation, we can see here the prediction. We can see here, as I did before, is the prediction which we have seen last time. You remember this page with P steps and so on. We have the reference work in which, again, I am considering D constant over the prediction horizon. And with this hypothesis, in this paper, is demonstrated that the solution is one. Quite similar as before, in which F3 we will see as in a particular matrix. if we have just one disturbance, let me say, is the column. Exactly, you remember when I considered exactly, but with a small change, appropriate change, which I considered, you remember the constant, yeah, consider U constant over the horizon. Of course, if D does, this is, if this hypothesis is not guaranteed, yeah, I don't know if there is a compact solution in this form. I don't think so. Since we have to calculate the solution numerically with a solver. Solver. You remember the last time I told you what a solver is? Do you remember Newton tangent method, Raphson Newton? Probably you heard about that. Let me speak about these three matrices, even though the matrix G is exactly the same. The matrix F11 is exactly the same, which we have seen very quickly now in the variation delta U. Interesting to look at F3. The F3, as I told you, is exactly the matrix which I introduced exactly today at the beginning, but instead of B, which is the map of the input, I have a D, which is the map of the disturbance. But otherwise, the idea is the hypothesis plays a crucial role because look here, this matrix here is calculated for U constant, CB, CAB, CB, and so on. And the last can be demonstrated. I don't have time to demonstrate, but if you look at the book, it is easy to see. But we have seen also intuitively last time, how we can calculate it. The reason is very shortly. Now we can see, if you k here, no, nothing changes. The first line. If you input k equal, you if input k plus one, I have to add these two contributions, and so on. I have to add these two contributions, and so on for the rest. And now instead of B, do you remember, I characterize the input D as a non-accessible but input. This means, assuming that D is constant, of course, the matrix F3 is exactly the matrix which I have seen, but instead of B, I have a D. I change just the map. Isn't a restriction, this hypothesis? Not really. Not really. Because very often the disturbance, not always, of course, very often the disturbance is slower than the dynamics, or we can consider in a controller which speed up the dynamics of the system in order to consider possibly valid the solution, and to use this equation here. What about d of k? In this sense here, d of k must be known, but I told you now it's not accessible, it's not measurable. Yeah, but could be, should be, must be estimated. Therefore, I will introduce also in this course the Kalman filter, which is a possible estimator, is an optimal estimator. Optimal in the sense, in the strict sense of the words. In the strict sense of the words. Because I try to find an optimal estimation, which we minimize what? The variance, let me say, roughly speaking, variance of the signal D. Of course, we estimate, better to say, the signal D, the disturbance, with the minimal variance. Let me roughly speaking with the minimal error, no? But the error is the variance now. It's a little bit more complicated. We speak about covariance, but let me at this moment say this. I need in a couple minutes again to stop the lecture, but I will come back really I have to call. I have seen that the people call me. Probably they want to say something to me for the meeting within 1 hour. But we will restart soon, considering the simulation, and through the simulation, as always, I will be able, I hope, to repeat a little bit, to clarify a little bit, uh, to yeah, to speak a little bit. Now, simulations. Uh, uh, yeah, simulation means MATLAB. Now I am totally confused because today, as always, we have so many meetings, boring meetings in an administration. As I told you before this lecture, in between the and to where is now MATLAB? 1 second. Why it doesn't work? Sometimes to manage everything, the lecture, MATLAB, parallelism. Oh, I need the other version. This is 17. 1 second. Why is blocked now? Why it doesn't work? I'm not able to open MATLAB. Okay, found it, found it. Okay, just a second to open. Now we will see with or without disturbance this delta variation. Why the delta? As I told you before, should be. Yeah, I don't have the demonstration here. It could be somewhere we have also the demonstration. As I told you in this course, the demonstrations are not important in the sense because we are more application oriented for different reasons. Cybernetic is in the application field, but in accordance also, or if you consider the constraints which we have in time. Of course, we don't have time to demonstrate theorems or so the method itself. Uh, you have seen, you realize that I try to sketch. Okay, with this excuse me, with these simulations or simulation, because is one in is two simulations in one file. uh, we conclude this chapter or this part dedicated to the MPC. Okay, let me. I don't know what you see. Let me see. Let me share because probably I didn't share. Yeah, now. In your folder, you can see. Let me see. MPC from the lecture. Yeah. You have a zip folder, which is this one here in my structure. Let me say I have here the corresponding folder. Okay, let me open this with the data. The data are exactly the same. The data in, the same, in which sense? The motor is exactly the same. This means I don't need to comment. You remember last time I told you resistance, inductance. This basically, inductance, as I told you, here is the inertia. You can see that this is a very small motor. uh, km Newton per meter divided ampere is this characteristic constant of the motor. No? This means what is the characteristic constant? From ampere to Newton per meter. Torque, because it's in a rotational configuration. Yes, we cannot perceive, we cannot see, but I am telling you. Or can represent also, how possible to say, the conversion between velocity to voltage. No? If you remember a little bit the model which I presented last time, this Km, let me show you a little bit quickly so we can understand. Let me. 1 second, I don't know where it is. Here. Also here, better probably physically. No? Here I called Ke apostrophe, which is equal to, we can see here, Km apostrophe. Apostrophe is just a way to distinguish between, if I remember well, radians in radian per second instead of round per minute or per second. This I don't remember. I have to check in the data sheet. But in any case, they are the same if you use, of course, the same unit. At least ideally, in an ideal mode, DC mode, just to understand, excuse me, what I intend with this Km. But I think I already told you 2 or 3 times. The matrix is the same. Yeah, yeah, we can see the matrix which I'm considering. Here, I didn't consider any disturbance at this moment. Here, I used the discretization offered by MATLAB. This is not exactly a feed-forward discretization, is an exact discretization. Now, about this topic, discretization, I didn't have time. I don't have time to go really in depth. I tell you a little bit when I will start inside. Let me say the Kalman filter a little bit more. But in this presentation, I think I told you at least of a feed-forward. Yeah, definitively, yes. Feed-forward Euler discretization. Here is not exactly this. If you want to use, you have to put some options. Otherwise, do you remember last time we have seen, I think here, how possible to say the discretization. I don't remember the Euler discretization, feed-forward Euler. But anyway, it's not now focused on discretization. You can use, let me say, theoretically, whatever you want, a discretization for this, for the project, of course. Of course, the discretization, nevertheless, is not irrelevant. What I intend, the method is not irrelevant. No? It's extremely important. But of course, we cannot focus on everything. But at least you have to know that you have different possible discretizations. And if you have different possible methods, this means we have always drawbacks and advantages. It could be that I will tell you a little bit during the next lecture, also a little bit today. But let me now finalize the MPC for a given discretization. For instance, this automatically calculated by MATLAB. Again, this is the name is exact discretization, the exact discretization. We can see here, for instance, alternatively, the discretization related to forward Euler. Probably this I told you last time. Really, I don't remember in any case, because I have seen exactly now the matrices in the presentation, and the matrices typically calculating feed forward is the most used for different reasons, which I will come back a little bit later. But also didactically, if the focus is not on the discretization, is the best in order to introduce the Kalman filter, in order to introduce MPC, in order to introduce everything. But of course, we have different solutions, solutions, performances. Let me say, it's not wrong to say solution, this, nevertheless. The matrix G, here, the matrix F2, is here. The matrix F3 is here. The matrix F11 is here, even though I don't use in this, if I remember well. No, I use, excuse me. This is the case, excuse me. This is the case of delta. No? F3 is relevant to compensate the disturbance, assuming that I know the disturbance, or I can estimate the disturbance. We will see with Kalman filter. Yeah. F11 is related to the input, delta input. In this case, we are looking for delta. F2 is related to U of k minus 1. We used, I forgot that we are in the case of T. No? This means in the context of delta U. Q and R is here, but I think I have the input of Q and R in the M file. Let me now open the Simulink. 1 second, because to open Simulink in my PC, it takes time. No? Yeah. I hope that will be open, because sometimes, yeah, let me share. Probably, let me see one thing. I don't remember if last time, 1 second, no problem here. I have to close the windows. I don't remember if last time, probably yes. I discussed this load. The load is there in any MPC application. We have a load because yeah, we have to know in advance, as I told you last time, the trajectory or trajectories. This means somewhere I saved the trajectory. And we can see here in a file the data trajectory, which we can find here in the file MAT. No? In the file MAT is the data file, which you can save vectors, any kind of data which you can load and use inside the program, inside everywhere, also in Simulink. We will see how. Here, for instance, we have this MIAT file, which we have a vector which represent the time, and we have another vector which represent the trajectory, and we will see here. The idea is to control, you remember last time I told you the velocity. Yeah. Let me now switch on Simulink. Let me switch on Simulink. The trajectory basically is here. I have to run the data. Otherwise, we can see that the Simulink does not recognize T vector, which is inside this MIT file. It does not recognize also the vector, the velocity, no? The velocity which I want to track, with the control with the system using our MPC control strategy. Yeah. And also here now we have the simple time which must be known. Let me run. Excuse me if I don't share, but it's not necessary to share because it's just to click to run. Okay. The system is the motor, which we discussed last time. Let me check test the software. I hope that this work without disturbance. We can see that disturbance is in the system, but we assume that it's known. Of course, this is an ideal assumption. Typically, we cannot know the disturbance, um, but we assume that. Of course, we can estimate, but we cannot know exactly as here in the simulation. But an estimation, do you remember I told you a little bit now, except for, let me say, an error in terms of, if you use, for instance, Kalman filter, a statistical error. Nevertheless, we can try to compensate with in this frame here. But of course, theoretically, it must be known or estimated with enough precision. Assuming that is not there, no, the disturbance. Let me analyze quickly the software here, which is quite similar as we have seen last time. If you go here inside, as last time, we can see that we have the current, which I can measure. We have the velocity, which I can measure, or I can estimate with the Kalman filter. We have here a vector which represents the time, but we have also a better way to represent the time. Now we can see here in the ramp, the time is in the ramp, and the sampled ramp. And then we have a UK minus one, because in this case we have a UK minus one. Last time this was here, but without any input. And yeah, the disturbance, if you have a disturbance. What I intend is this one. Last time, I don't know if you remember, this was not connected. Here represent a UK minus one. This means UK delayed of ensemble. Here inside, if you go here inside, you can see that we have a block with delays the signal of 1 TS, no? TS. You can put also 2 TS, 3 TS, but we have a K minus 1 multiply TS. This means it's delayed, considering with respect to the normal signal of 1 TS, 1 sample. Okay, if you go here inside, here I'm using again this interpreted function because this material here was realized with interpreted function. We have also a different implementation using embedded function. For some reasons, could be better because I can flash the program directly in microcontroller. But in my opinion, sometimes this interpreted is for didactical reason is nevertheless useful. Let me go inside here in this interpreted function. I don't know last time, do you remember? It's an M file. If you want, I can share. This is the file. The file, if you remember, is basically a copy of the solution which I presented also today. Again, T0 is our time. This is the state, current, and velocity. This is the old solution. This is the old solution. Is in our case we will see now a little bit better what this is. D is the disturbance. Here I round. I mean, I will build this integer. Let me say counter. It could be also better organized, but I didn't change now at this moment. It's the ramp divided ts plus 1. We start from 1 basically, and we round because not necessarily is an integer value. Here is the let me say vector of the desired velocity. We can see that we have 4 steps. We predict 4 steps. Here is the solution. If you remember, this is the general solution of the unique the solution which calculated the global minimum. Remember, I told you last time a little bit more theoretically than today. Now d is equal 0. This means this part is not there. We will see if I include, because if I don't connect d is equal 0. And look here, the output here is commented very well. Here is commented very well. The output, which I have to calculate to be applied to the system, is not delta, but is u. Anyway, I will find the solution for delta, or with respect to delta, but I apply to the system the u. But this is not difficult, because when I have a delta, we optimize, which which optimizes my which is the optimal solution. I add delta plus the previous solution, which was already optimal, to obtain u of k. I don't know if this can be understood, in which UA, now we can understand what this is the previous solution. It's the previous solution. Each time I will add to the previous solution the new optimal delta. Because to the system, I have to give a u. Okay, let me run. Now, you remember UA 4 is the position of in the max. Let me probably analyze again this. Could be useful. This one. UK, this output is going here, which is UK minus 1 plus delta. If you remember inside, here is UK minus 1. To be precise, the delta is in a vector. I consider just the first element of the vector. Do you remember? The rest I will throw away. Let me come back on this in order to understand better. As last time, here, the delta is just the first element. Because you remember, I told you also today, also last time a lot, The model predictive control calculates the vector in terms of u or the delta u for the future. But of course, I have to apply just the first one. And this UA is the previous one. But U, not delta. Huh? Because the delta is just an auxiliary variable, if you want, to optimize. Each time I optimize the input for the system using optimal delta each time. Therefore, here old voltage input from MPC. Think about it. Huh? Each time I calculate delta as an optimal value, and I sum up to the previous UK minus 1, which is not a delta. It's already recalculated because I'm considering each time UK minus 1 plus delta to be applied to the system because I applied U, it's not delta. Okay, let me simulate now and then we will conclude. We do 2 simulations without disturbance. You remember last time I told you also with the easy structure, this is the U variant. Nevertheless, we are able to compensate the disturbance. We will be able to compensate the disturbance. But you remember, we have to use a large Q, a very large Q. The effect of this, we have a very large U. Here, in the presence of disturbance. Here, the disturbance is not present. Let me see what we have. We have just an error at the beginning because of the initial condition. It could be that Q and R is not optimal. Or we can see a strong reaction very quickly, starting from a very large error. We have this dynamics. Let me introduce the disturbance now. Before I introduce the disturbance, look at the input. You remember last time I told a lot about the input, no? Because to compensate with the old structure, the disturbance, I need very large Q. Here, we don't have disturbance. This is a little bit the results. At the beginning, we have an error. This means isn't a disturbance somehow, because it's not exactly the goal. Now we can see here how the disturbance looks like. It could be not acceptable. Now, if you introduce the disturbance, we will see that the situation is, in any case, will not be better. That, of course, depends on the value of Q, how change. But if you consider here disturbance, exactly in the input, you remember I told you last time, in the second channel, we have the disturbance, which here we have a vector. And if you look here inside, in order to understand, we can see this, the matrix B. Mm, CR, I don't remember what was. Let me see 1 second to understand better. I will tell you in 1 second. Okay, 2 times 2. Let me come back here. Oh no. Um, I lost. Okay, now I see. Um, mm. Yeah, it seems to be that we have a disturbance in the electrical part. You can consider in the electrical. Last time we consider here, do you remember minus one divided j? Yes, conceived in a different form. Let me see if everything is consequent. Because, yeah, here I show you why it's consequent. Because DD at the same structure of B. It seems, in accordance with this simulation, last time, do you remember, we simulated the disturbance in the torque. Minus 1 divided J, I think, was something like that. We have to check, but it seems to be something like that. Here, we have the disturbance in the electrical part. In fact, DD is exactly like B. The same map as the input. Did you see in the matrix B in the Simulink, we have 1 divided L, 1 divided L, and then 0, 0. This means the disturbance in the electrical part could be. If you don't like, you can put in the torque, but in this case, you have to change. You have to change D. D becomes, or the DD, DD becomes TS, please pay attention, which multiply 0, first component, semicolon, minus 1 divided J, as last time, if I remember well, as last time. But the disturbance could be everywhere, no? Everywhere. Okay, let me run. The disturbance is not compensated, but is nevertheless compensated because the system, you remember last time, react, but not so well. I mean, to compensate, I have to increase Q, and this I have to increase U. Do you remember last time? Now, if I observe, if I estimate D, this means if I have a Kalman filter, if I have an observer, which we can see here, for instance, estimate somewhere the disturbance now is in an ideal situation in which the disturbance is totally known. The disturbance is totally known. Of course, this is an ideal situation, never happens. Let me run, we will see that this is the result as before, no? As before, with the same, let me say, U. With the same, this is the result. If you want to check at home, U, no? But of course, if you want to compensate the disturbance without estimating the disturbance, you need a very large U. Sometimes impossible to be realized. Sometimes it's possible. Therefore, this scheme is also important. But again, you have to estimate the disturbance. We cannot know the disturbance. Yeah, didactically, now the idea is to show you the principle. The principle. Okay, I have to stop because I have to go to a meeting. I hope to be here half past. We can exactly uh, consider to meet again half past. I will start with a new topic, and the topic is observer. The topic is Kalman filter in the sense. Okay, I think we can conclude here. We will see in half hour.